Hello. So in the previous video, I have tried the best graphic devices, pen and paper, to introduce the intuition. So I realized that it would be nice to have a clean PowerPoint slides, graphics on the slide, but it takes too much time. I need to record it today, and I think I don't have enough time to do that, so I used paper. And but I prepared there. I have a tablet. I tried this at the beginning of this semester, but does not work well. And I tried another device like this. So when so you can, if you put a mirror here, so then the iPad can capture the image on the desk. So this is a device for my son, but I could use this for the graphic illustration, but it does not fit on my phone. I have an iPad, but transferring, I just wanted to use my phone, and yeah, this is just out of my laziness. Let me know if you if you had any problems with the previous videos. I may try a whiteboard. My son has a lot of devices. He has more graphic devices than I do, so I can steal his whiteboard and show you the crafts that you need. Anyhow, back to the point. I have explained this, so I explained this, and now let me explain the intuition why omega inverse is the optimal weighting matrix. The idea is also straightforward. As I said, what you have to do here is you have to put more weights on informative moment conditions and put less weights on trivial moment conditions. And the amount of information, which moment is more informative? The informative moment is defined by the variance. So some moment may have a lot of noise, so that moment will have a large variance. Meanwhile, some other moment conditions may be more accurately estimated, so it's more informative and has little noise, and then that variance will be smaller. In this case, so if you have two moment conditions with larger variance and smaller variance, the smaller variance moment condition is more informative because it has less noise. Then you have to put more weights on the smaller variance moment. To do that, we are taking inverse of the variance. So if you think about the variances, so say the first moment has a variance of 10 and the second moment has a variance of 1, then we interpret this as the information in the first moment condition is 10 times less accurate than the information in the second moment. Therefore, we are going to put 10 times more weights on the second moment, right? We take the accurate moment condition more seriously. Therefore, the moment condition will be the inverse of their variances. So if the variances are the same, of course, all the moments will have equal weights. And if there are covariances, then also the covariance is taken into account, but the explanation becomes less intuitive. So the basic idea is which moment is more useful in your estimation, and the useful moment is from the moments that has smaller variance. Okay, so we learned what is the optimal weighting matrix, and then it is just, again, it is a pure theoretical result. Theoretically, okay, it makes sense. And however, then how can we calculate? So to get this optimal weighting matrix, you have to estimate omega first and then take inverse of that. So inverse is not a big problem, But how can we estimate omega? Earlier, to estimate omega, we considered this method. So omega was defined as the population mean of the moment, gi theta 0, gi prime theta 0. So population mean is easy to handle, but theta 0 was the problem, and we replaced theta 0 with theta hat, the estimator. The resulting estimator was used to estimate omega hat. But it was okay. So in this chapter, in this section, when we consider the variance estimation, theta hat is available because we estimate the variance after estimating theta. So theta is estimated, then we study what is the standard error of that estimator, then you need this, and you can use this. However, now we are studying optimal weighting matrix section. That means you have to define the optimal weighting matrix before estimating the parameter. Therefore, this method does not work. Theta hat is not available at all because you have to do this. You have to find W before estimating theta. But you need the result of theta, so you need the result before you do the estimation. So it doesn't work. Of course, there is a solution. The solution is we have to have some theta hat before estimating, before using the optimal weighting matrix. So the idea is like this. Before the optimal weighting matrix is calculated, we are going to estimate theta twice. Before using the optimal weighting matrix, just use whatever matrix you want. Whatever matrix, say the identity matrix. Of course, it has to be positive definite, strictly positive definite and symmetric. So any symmetric positive definite matrix as the weighting matrix, and find a theta hat or theta tilde. So theta tilde is the first step estimator using any matrix, but usually the identity matrix is used because it is the easiest way to find the simple estimator. And then then we learned theta tilde is consistent even if it is not efficient. So theta tilde is efficient, then it is consistent, excuse me. So theta tilde is consistent. So plug this in here. So if you use theta tilde here, omega tilde will be consistent for the true omega. So consistency is what we need. So then using that omega tilde, obtain the weighting matrix W tilde by inverse of the omega tilde, and then use this weighting matrix and re-estimate the GMM. So estimate the second step GMM matrix uses the optimal weighting matrix, an estimator for the optimal weighting matrix, and the final result is theta hat, and using this theta hat recalculate the variance estimator. So the variance estimator must be can use the second step estimator again. So you are like repeating omega estimation and theta estimation, and then omega theta. So in the literature, there are some extension of this, like you can do it more than twice. We start from the identity matrix, and so identity matrix, and then estimate theta, and from the theta estimate the weighting matrix. From the weighting matrix, estimate theta again, and then again and again and again and again. It is called iterated GMM or continuously updated GMM, something like that. It makes sense, but it seems that the iterated like more than 2 times has little improvement. So usually just 2-step is enough in many cases. But you may try in your paper if you're interested. Okay, Let me call this a video, and we'll continue a simple application to linear regression model in the next one.